Hey everyone, in case you needed a quick review or if you are absent from class, here's your lecture on research strategies. This will cover all the information from the early concepts through experimentation. If you need to review any of the quasi-research methods or statistics, please see the next video. When we talk about the scientific method like we did in class, we're talking about a 5-step process. This 5-step process is meant to address all types of research, not only experimentation. So when we talk about the fact that we create or construct a question like a hypothesis, we control the conditions as best we can, we try to remove biases, and we generate results or data. You're talking about the scientific method, essentially a methodology that dictates how we should do research. Ultimately, we'd like to put things into an objective, non-biased pass-fail test. And in that case, we're often talking about experimentation. We're going to use the term empirical quite often in this class. And empirical will always mean verifiable by the senses. You can touch it, you can manipulate it, you can collect data on it. And when we talk about empirical investigation, we're talking about collecting data by making careful measurements based on direct experience with. So it can be something like heart rate. It can be the number of times someone blinks, but it has to be something that you can actually physically collect the data on. You can see it, you can manipulate it, you can prove that it is. That means that we want things that are experience-based, not speculation. So to test something like our memories, if we say memories work like audiovisual recorders, well, we can empirically test that. We can set that up into a pass-fail scenario. We can look at elements and find ways to collect data on it. So it's no longer just our best guess, but it becomes our ability to prove and develop a theory about it. Theories, or specifically scientific theory, we're looking at a testable explanation for a set of facts or observations. The social learning theory was a testable explanation for the idea that we learn by watching others. Monkey see, monkey do. Now, obviously, that feels like common sense. We watch people, therefore, we know what they're going to do and we mimic what we like. But Albert Bandura decided to put this in an actual experiment. He took children, he exposed them to a scenario where they watch an adult get upset and then throw a tantrum by punching a clown, well, a blow up clown, and then put children in a environment that would induce the same amount of stress and frustration and watch them repeat almost exactly the language and the behavior that was expressed by the adult. He set up a control condition where those children were frustrated but not presented with the clown and they didn't show the same behavior. So again, it's a theory. It is an explanation for facts and observations. Often we will use experimentation to confirm our theories. There are some things that you should be concerned about when you're doing research. The first one is the hindsight bias. And again, this is the I knew it all along phenomenon. Hindsight bias is the tendency to believe after you know the end result that you could have foreseen it coming. We do this a lot in history, where we will say history repeats itself. We should have known that the housing crisis was going to happen. We had all this information. Why didn't we just stop it? And again, if we had known that the housing market was going to collapse and that all these people would be losing thousands upon thousands of dollars in homes that they overpaid for, no one would have done that. But after we knew that the housing market crashed, we could go back and we could identify all of the events that led to it. It's like on a Friday afternoon saying that your football team is definitely going to win, and then coming back Monday morning and going, I knew they were going to lose. I knew it all day long. I knew it as soon as I watched them step on the field. Well, you knew it because now you know how the game ended. People will often do this with Pavlov's experiment. Once exposed to the fact that the dog made the association between the bell and the food and that yielded the dog salivating to a bell, people go, well, that makes sense. I knew that before. You didn't have to set up an experiment. But the crazy thing is, no one actually put that together prior to the experiment. Be careful with overconfidence. Again, this is something we have to look at when we're doing research. We have a tendency to think or be more confident in what we feel we are correct about. And you've probably had the sensation when you sat for a test and you looked at the material and you're like, I know this. I'm so confident that you didn't go back and check your work. You didn't carefully read the questions. And lo and behold, you get your test back and you feel that maybe you did really poorly. Well, we tend to overestimate what we think we know and how confident we should be in what we can do. But again, it's because not knowing or having to profess that you don't know sometimes can be really uncomfortable. Overconfidence can also lead to something that we'll later talk about, which is the false consensus effect. The false consensus effect is the tendency to overestimate the extent to which others share our beliefs and our behaviors. This one you might find when you are in class and somebody professes, well, the entire class agrees with me. And you think to yourself, I don't agree with you. I've never shared a thought with you. But that person probably sits surrounded by people that are very like-minded or people that they appreciate being around. And those people probably confirm what they think. And so they assume it ripples further outward and everyone agrees with them. It's easier to see, I think, in politics, where if you look at any political group right around election time, they will say to people, so you could take the Democratic or the Republican Party, you can take whomever you want. And as they're talking to a group of people, they're often surrounded by party members, people who believe what they believe or at least kind of fall in line with their thoughts. And they will say things like, the American people believe like we do, and they will put out their belief. And you can turn the channel to the exact opposite political party and you'll hear the same thing. You know that the American people believe the way we believe because. And what they're doing is they're assuming because they're surrounded by like-minded people that more people agree with them than disagree with them. Much of what we're looking at for the scientific method should be a review for you. So on the test, if you see anything that talks about two variables that are going to be tested against each other, you're looking at a hypothesis. So for the scientific method, the very first step is developing a question, developing a statement, and having a focus for your research. The statement has to describe the relationship between variables. Now, often we'll talk about between an independent and a dependent variable, but at minimum, two variables must be involved. Both of those variables, the independent and the dependent, have to have operational definitions. So in class, I ask you something very simple like, can you bake a cake? Someone always says yes, and then I say, okay, what would you do to bake a cake? What are the ingredients? How much do you need? How long would you bake it? And without a recipe in front of you, most people give general things like you need some sugar and you need some eggs. Well, with that kind of definition to your baking, no one in the class can replicate your results. But if you had something that kind of follows more prescriptively, like a recipe, I need 3 eggs, half a cup of sugar, a cup of butter. You could take that information and replicate the same cake throughout the entire classroom. Well, we're not talking about cakes, we're talking about experimentation. So we start with something very simple, like if students were to get more sleep, they would get better grades. It's put in an if-then statement. It sounds like a hypothesis. The only problem is, what do I mean by more sleep? My independent variable doesn't have a definition. It needs to be clearly defined. And get better grades. Well, is that an 81 on a quiz to an 82, or does it have to be more significant than that? So the dependent variable also has to have a definition applied to it. We need to make sure that what we are measuring is very clearly defined. Because, and it's a statement that's really, really important, operational definitions allow for the replication of an experiment. So what you see here in red is a very important statement to memorize. Operational definitions allow for the replication of the experiment. Now on your test, you will get questions or something very similar to, Andrea is doing research on anxiety, and she chooses to look at anxiety as an increased heart rate. This is an example of, well, anxiety being defined as an increased heart rate, the increased heart rate, that's your operational definition. Anxiety is a whole lot more than just an increased heart rate. But for the purposes of that question and that scenario and that research, anxiety had been defined as increased heart rate, which means that we can look at a whole host of a variety of behaviors and concepts as long as we very clearly define what it is that we're looking at. Once you have your hypothesis, you need to actually run your experiment. Now, I know that we're kind of skipping over things like procedures and all of that, but we're kind of try to get to kind of the most basic of all this. So please know that your independent variable is going to be the thing that changes within your experiment, and it's in your experimental condition. The big thing with the independent variable, if given the opportunity, you want to have the presentation of that variable be as random as possible. So in class, we looked at Rosa's experiment and we looked at therapeutic touch. And the gist of what she was doing was whether or not people could sense a human energy field by placing her hand over their left or their right hand. Well, that was her independent variable. To ensure that a pattern didn't form, to make sure that the presentation was random, she would flip a coin to determine whether or not her hand would go over left or right. It prevented this pattern and it prevented people from trying to guess her pattern. So, random presentation, a process by which chance alone determines the order in which a stimulus is presented. Randomization, or making something random, it's like pulling names from a hat. It's a really good way to describe random. You want to make sure it's done without intent. So anything that is random, there is no intent, it is done without intent. As you're doing your research, you're going to start to gather your data. Data is going to be generated by looking at your dependent variable. So your dependent variable is going to be the variable that is going to exist in both your control and your experimental group. Your independent variable is only in the experimental group, and you use your dependent variable to measure it. In your control group, you will still have your dependent variable because you will still be getting a baseline measurement. So data is going to be the information that you gather, and your dependent variable is going to be your measurement. Your dependent variable must also have an operational definition. As you're conducting your experiment, there's more than one way to actually set up your experiment. You can do something called a within subjects design or a between subjects design. If you can clearly set up a control group and a separate experimental group, you're doing a between subjects design. But sometimes you may have certain constraints where you want your control group and your experimental group to be the exact same group. Say you're doing drug trials and you're trying to give someone a medication to stop smoking. Well, you may want to run your control, see what their baseline data is, then provide the exact same group of people with the medication and see if it reduces their smoking behavior. That would be a within subjects design. If you wanted to see whether or not an educational practice would be best within a classroom, you may want to randomly sample from the entire school, randomly assign your sample to a control group and an experimental group, and then compare the two groups to each other when you run the program with the experimental group versus your control group, which wouldn't have the program. That would be between subjects. In other words, you would have two separate populations, two separate samples, and you would compare the data between the two. It is possible to run experimentation that allows you to manipulate more than one independent variable, and also to gauge or get data from more than one dependent variable. The reason we don't do this in high school is due to time constraints and because often we want you to see the outcome of the experiment. One of the most important statements to come away from this is going to be that experimentation is the only research method that allows cause and effect relationship statements to be made. You will later hear me say correlation does not equal causation, and that's because many people confuse correlational studies with experimentation. In experimentation, you manipulate your independent variable and you record the change by the dependent variable. If A then B, you can see that one causes a change in the other. Correlational studies do not do this. You see two variables and you track the relationship between the variables. Do they change together? How closely do they change together? But you can never say that they impact each other. The other thing that we look at when we look at any research method is that all research methods come with a certain amount of drawbacks. Experimentation also has drawbacks. First off, experimentation is not necessarily applicable to every single problem. If you wanted to do research on, say, smoking behavior, and you wanted to run an experiment, you might be asking people to manipulate their smoking behavior. If you were to truly set up a control group and an experimental group, you would have to do it randomly without any intent, which means you might put non-smokers in your experimental group. You might have to ask non-smokers to smoke. That becomes an ethical consideration. You can't inflict harm or intend to expose people to harming conditions, even if they volunteer to do so. The other problem is that often experimental setups feel artificial. you can't really mimic 100% real life in an experimental scenario. So you find that sometimes the results don't really translate well into the real world, or it feels too artificial to actually make any sense. Once you've run your experimentation, you're going to statistically analyze your data. You're going to find out whether or not your data was significant and a real change occurred. You're going to figure out what your measures of central tendency are. You're going to figure out whether or not your hypothesis was truthful or if it's what we'll call a null hypothesis. Finally, you end up having to publish your work. So for experimentation and generally all research, you have to publish your research so it can therefore be replicated and also reviewed by peers within your field. What you're going to find is that you guys will have a reading here shortly that questions whether or not we fund replication research as often as we fund new research. So replication allows us to state that if we can replicate someone's experiment and the data essentially holds true, that the experiment or the results of the experiment are accurate. They're without bias. So replication allows for us to give validity to our research. If the data continues to show the same pattern, trend, or output, we assume that it must be good research. This should feel like more review terminology, and we're still talking experimentation. You heard me say several times the experimental condition and the control condition. In the control condition, the subjects do not get the independent variable. In the experimental condition, they do get the independent variable. It is only within experimentation that we talk about a control or an experimental condition. While conducting research, you may come across extraneous variables and confounding variables. Remember, as I said in class, I will never give you these two terms in the same answer set for a question. So, an extraneous variable, if something is extraneous, it's extra. Extraneous variables, there's an additional variable that has been introduced into the research that may have had some form of impact on the dependent variable. So I decide to run an experiment and I use two different rooms. And in my room, the temperature is a comfortable 72 degrees. However, in the next room, the air conditioner is blasting and it's broken, and so the temperature in the room is 47 degrees. It's frigid. The change in temperature, while not part of the experiment, may be a variable that impacts how the subjects perform. That would be an extra or an extraneous variable. Sex, your race, room temperature, all of those things that you might not be able to control, may unintentionally have an impact depending on what it is that you're studying. Confounding variables, to confound something means to confuse it. So a confounded or a confounding variable confuses what the actual independent variable is. So I gave you guys a question that looked at confounding variables on your handout. If I have Andrea, again, who wants to improve her standing at her job, she wants to get a raise. She decides to bring in cupcakes on Fridays, she works every weekend, and she decides to go to a workshop seminar. And lo and behold, 2 weeks later, after she's been doing all these things, she gets a raise. Can you tell me what caused her to get the raise? And if the answer is no, then what you've essentially figured out is that it might have been the cupcakes, it might have been the working the weekends, it might have been the seminar, but they're all confused together, so we can't say what really directly caused the increase in pay, what caused the outcome. When we look at experimentation, it's important that you understand population, sample, random selection, and random assignment. The population is the entire group of people from which you want to be able to discuss from your research. So it could be all of the United States, anyone that suffers from depression, Kettle Run high school students ages 14 to 18, whatever it might be. Once you've defined your population, you are going to at random pull a sample from it. Your sample should look like a mini version of your population. In other words, if you break it down to the percentages should hold true. What I mean by that, let's say we want to look at a group of 1,000 people, and in that group of 1,000 people, 50% are male and 50% are female. 70% are Caucasian, 30% are African American. 20% are Jewish, 30% are Muslim, and 50% are Christian. Whatever your numbers might be. And these are just off the top of my head. Well, of that 1,000, I'm going to pull 100 people. Of those 100 people, 50% should be male, 50% should be female. 70% should be Caucasian, 30% should be African American. 20% should be Jewish, 30% should be Muslim, and 50% should be Christian. So that 100 should demographically look like that 1,000. Then I'm going to randomly assign those 100 to either my control or my experimental group. And again, it's going to be without intent, like pulling names from a hat. I'm going to take all 100 names, cut them up, and put them into a hat and randomly and blindly pull them. So I'll end up with 50 in my control and 50 in my experimental. Now this should control for confounding variables. It should make sure that my control group and my experimental group look very similar to each other. I should have my control group with 50% female and 50% male, and my experimental group with 50-50, meaning that all of the variables are equally distributed. They might not be distributed in the exact same way, but they should be equally distributed between the two groups. What I mean by not in the same way is I might have a African American Christian female and a Caucasian Jewish female in one group, and then in the other group I might have the races and the religions mixed between the two people differently, but ultimately it all ends up working out where they're equally represented in each group. Again, your population is the biggest. Your random sample is what you pull from the population, and from your population you will randomly assign people into your control group and your experimental group. As simple as this sounds, this is something that people tend to screw up on, so make sure that you understand that when we say random, we mean without intent. The sample is what you pull from a defined population. You have to know who you're talking about. And then again, assignment is that you, at random, without intent, assign people to either a control group or an experimental group. The last thing that we talk about is that once you've done all this, you will generate a report. It'll have your procedures. You will then, with your data, make everything simplified and present your results as statistics, and then have a discussion about what can be done to replicate this research. You're going to subject it to peer review and hopefully have someone go and validate your research. As you continue on, we will talk about other forms of research. Please understand that they are going to come with drawbacks as well, but sometimes they're more appropriate than experimentation. Experimentation is the most well-known of the research methods because we teach it so often. The scientific method should be utilized not only when we're talking about experimentation, but applied as closely as it can be to all forms of research. Generate a hypothesis or a question that needs to be answered, collect data, avoid bias, etc.